Hello students, welcome to e-learning. Today we are going to learn Hooke's law and stress strain curve. So the contents today we are focusing on are stress strain curve for mild steel, means low carbon content steel, then ultimate stress, breaking stress, and Hooke's law. So first we will try to understand, before going for simple or a stress strain curve, we will first understand exactly how the test is conducted. So a test specimen is taken, mild steel test specimen with a length. So here you can here the tensile load is applied and it is pulled. So you can find out the changes happening in the bar or a steel or specimen. So before going again to the specimen, we will understand this graph here or the legends for variation in stresses. So this blue color at the bottom is low stress, or you can say nil, zero stress. So it is as the tensile load will increase, the blue color is going to change to sky blue color, then green color, then yellow, orange and red. So it means the stress levels are increasing here in the bar. These colors will indicate. You can find the changes in the extension. See, it is now green, it is turning to yellow slowly, and then now you can find out orange color, red color, and here it breaks, right? So similarly, this is very helpful in understanding how the stress is developed in the specimen, test specimen. So this tensile loading or tensile test is carried out to find out stress strain curve of mild steel. Okay, so you can find out now. See, slowly the load is applied. Okay, the extension, original length of the bar is increasing, correct? It is increasing in the length. Also it is going to reduce the diameter of the bar here, or the cross sectional area of the bar. It is going to reduce the area. You can find it now. See, slowly the neck formation, it is reduction. See, this reduction in the diameter is nothing but the lateral strain, you can say, and increase in the length, you can say it is linear strain or longitudinal strain, right? So load is going to develop or increase the stress levels. So you can find out the blue color, the color variations are telling us how the stress is increasing, and due to that increase in the stress, the failure is taking place. So see, find out again, we'll understand, try to understand. See, it is now blue color, it is slowly it is turning to green. It means it is at this level, right? It is again, see, at this level, at yellow color level, then again the stress is increased. See, neck formation is there, red color, and breaks, the bar breaks. So this loading or the tensile specimen, test specimen, is going to help us to understand this stress strain graph. Okay, so you can find out at the x level, x axis, the strain or the deformation is given here. Strain is given at the base and stresses in y direction. Okay, the stresses may be in Newton per millimeter square. Strain doesn't have any unit. The test specimen is this with the initial original dimensions. and you have found out the stress was increasing, strain was also increasing in the bar test specimen in the previous slide. So similarly here, as the stress is increasing, the strain is also increasing in the bar slowly. It is rising, and you can find out at this point, okay, the stress is so much, right? Stress is say considered 10, and strain is also something, right? Strain is also this much, say consider x extension in the bar, right? So for this stress, this much is the strain, right? So what they have written is proportionality limit or proportional limit. It means hereafter, if stress increases, strain is not going to proportionally increase with the stress. Okay, strain is not going to be observed the same as it was happening till this, because say consider the stress is increased, say consider 5 value, then strain is also going to increase with, say consider 2 value. Okay, so strain is 2 at 5 level. Similarly, at 10 stress, it is going to be 4 value of strain. Okay, because it is going to be stress was 5 and strain was 2 here. Again, if it is doubled, say consider stress is 10, strain is also doubled. Okay, that is 4 value. Similarly, this happens, stress is proportional to strain. It means the stress increases, strain also increases. Okay, so this happens till the proportionality limit. After this, it is not going to be the same. The stress levels are going to increase, or strain is going to reduce or increase. It is not going to be in proportion. Okay, so till this, say consider this point is said to be proportional limit point. Thereafter, again the load is increased, it means stress is increased, and you are finding there is also increase in the length or deformation or strain, right? So this point is said to be yield point. You can find out there, here it is written. So yield point, leader line is showing us the yield point. So yield point means hereafter the elastic phase of that material is going to convert or transfer into plastic phase. Okay, elastic phase means wherein if you take out the load, or take out the load, it is going to again come back to its original position, original shape and size. But hereafter, if you again increase the stress or increase the load in the specimen, it is not going to again deform or come back to its original shape and size. Okay, so it has been converted or changed into plastic phase. So again the stress levels are increased. You can find out the increase in the length as per as compared to this original specimen, right? At this level, okay, the increment has been taken place, means the strain has taken place. Coming to again increment in the length, increment in the load, you are finding out there was the neck formation. See, you can find out the reduction in the area, cross sectional area of the bar, right? So this is here, you may find hereafter, you may find in this region, you may find what, the neck formation. See, here also they have written from yield point to ultimate point, strain hardening takes place, and thereafter the neck formation starts. So here you can find the image. It is showing ki baba, here at this point the neck formation starts, and after neck formation the load is automatically going to decrease. Okay, because that particular material is not going to have that capacity to resist the load which is applied. So it is going to reduce, and at this point it is going to break. Okay, that material is going to break. So this is how the stress strain curve forms for low carbon steel, or you may say MS bars, that is mild steel bars. Okay, so you may find at this point there is yield load, right? Load is nothing but load increases, load is directly proportional to stress, right? So if load increases, stress also increases. So you may find out yield stress at yield point, this yield load to the cross sectional area of the material. Okay, or you may find the cross section of the bar, you may find there is yield stress. Okay, yield point stress is known by P by A, right? So that is load by area. So yield load divided by area is yield stress. Coming back to ultimate stress, so this is the highest point, highest load applied on the material or the bar. Okay, so that ultimate load divided by area is said to be ultimate stress developed at that in that material. So coming back to the failure load or the breaking load gives us the stress level at that in the material at that particular fracture point. Okay, so breaking stress. So we'll continue in the next slide. So here also you can find out the same, this is nothing but the same graph of the bar, MS bar, but here you can find out the regions of where the plastic region and elastic regions are formed. So you found out that the proportionality limit is at this location, wherein till this point you may find linear and elastic straight path of the stress and strain, because stress is proportional to strain within this limit of proportionality. Okay, in this till this, then you may find out here the bar may be elastic but no longer linear. Okay, or no longer linear in the sense the curve is not going to be straight line like this from this proportionality limit to further and further. Then coming to the yield point is going to tell us that this is going to the material is transforming itself from elasticity to plasticity phase. Okay, so within this limit you may if you unload or if you take out the load from the material, it is going to regain its original shape and size, and further from this point if you again apply the load and again take out, it is not going to come back to its original shape and size. So this is hereafter from this region, this is called as plastic phase. So this is said to be elastic region, elastic limit we call it as. So till yield strength, this is said to be elastic limit. Okay, so you may find out, see here also they have written once stress is removed, returns to its original shape and size in elastic limit, and plastic region permanently deformed by the stress. So it is going to be permanently deformed, means it is not going to come back to its original shape and size. So next we will come to Hooke's law. Hooke's law states that stress is proportional to strain within the elastic limit, or it is said here as strain is proportional to the applied stress. I said stress is proportional to strain, here it is said strain is proportional to stress within the elastic limit. So you may find out here there is an example taken. So there is a spring with its original dimension, this is the neutral line said to be 0. When load is applied with F, so it is the elongation or the deformation taken place is X. Similarly, means this force is nothing but the stress applied and the strain taken place here, right? X is the strain taken place. So stress is proportional to strain. So you can see F is equal to Ks. So what is this? K is nothing but the spring constant. This will discuss in we'll discuss this in this further coming slides. So you may find out again this stress is increased with twice, stress is increased double, it is doubled, so the strain is also doubled. Okay, so what is happening, if stress is 2, then strain is also 2, right? So this happens only in elastic limit. So Robert Hooke, who developed this law, tells us that stress is proportional to strain within elastic limit. If stress is 2, strain is also 2. If stress is F, strain is also X. It is not varying, so it is proportionally increasing. So stress is proportional to strain. So F is nothing but force applied on the spring, and K is spring constant, and X is extension of the spring. So what is K? You will understand what exactly it is. So this is nothing but the spring constant. Say consider this 2 or 2x. This 2 is nothing but the constant, right? So this is similarly this spring is pulled, and it is the pulled with double force. So that double force is nothing but K here. So that double 2 is nothing but the constant, spring constant. Okay, so say consider, we will understand like this in simple manner. Say here it was 1x, here it is f1f, right? So nothing is there means it is 1 unit. So 1f is equal to 1x, it means 1 stress is equal to 1 strain. Here it is 2 stress is equal to 2 strain. So this is how you have to understand very easily in simple manner what is exactly the spring constant. Okay, so spring constant here. So now we will come across the proportionality limit. So this was the first point in the previous slide, what we learned in stress strain curve. So this point was limit of proportionality, and you found that within this you found the elastic limit. So within this elastic limit, what does this Robert Hooke states, or Hooke's law states? Stress is proportional to strain. So this is elastic region here. So stress is proportional to strain. So you have found out here in this example of this spring. Similarly happens in the bars, in the bars or the metals or the steel which is used in the test specimen. So Hooke's law states that stress is proportional to strain. This is proportionality sign. So what is this K? You can replace this K with the elasticity constant, because this is happening in the again, why I'm telling in very simplest explanation, how to remember why how does this E comes, or elasticity, Young's modulus of elasticity, E. This is nothing but the elasticity constant, because this happens only in elastic limit, right? So that elastic constant, if this much is this stress, this much is the strain. If this much is the stress, this much is the strain. So that particular proportionality or the elasticity constant should be maintained. So it is multiplied for that particular strain. So stress is equal to capital E into strain. So you can also reform this stress is this equation as elasticity, modulus of elasticity is equal to this strain. You can drop it down to the bottom of stress. Okay, that is denominator. So Young's modulus is given by stress divided by strain. So this is how the Hooke's law is formed here. Stress is proportional to strain within elastic limit is very, very important. Okay, so thank you students for listening patiently. For further notifications and videos, interesting videos, you can subscribe the channel